This is Knowledge Engineering with Semantic Web Technologies, and this is lecture number 4 about OWL, rules and reasoning. So about what will we talk in lecture number 4? We will cover here the top layers of the Semantic Web Technology stack. And in these top layers you have languages which express models, like for example OWL, and you have the so-called logic layer, where we also will talk about rules. Let's have a look at the content. First, we start with RDFS semantics. We have already talked about RDFS, but we haven't defined a fixed semantics for that. So we will first give an answer to the question, why is a formal semantics for RDFS really necessary? And then, of course, we will define it. And then we will learn about a more expressive language for ontologies, for expressing ontologies. And therefore, we will cover the so-called web ontology language OWL. And we will learn how to define classes, instances, and properties in OWL. And we will also learn how to define complex classes and how to define property restrictions. And then we learn something new. We learn something about role hierarchies and the so-called general role inclusion, with which you have the possibility to chain properties to each other and to define more complex properties out of simple properties. So this is something really interesting, this concept of the so-called general role inclusion, which enables a large or huge expressivity of this language. And then, of course, we also have to talk about rules. So we will talk about what is the difference between what we already know here in description logics and OWL, and why rules really are more. So the question is this really more than description logics? Can I express things with rules that I am not able to express with description logics? We will see that here, of course, the problem in the end will be that if we really include this higher expressivity, then this results in something which is in the end undecidable. We know this already for first-order logic. We know that most of the general inference algorithms, we know there they are undecidable, so they will not stop for all situations and all possible knowledge bases. And then we put everything together in an example, and you will see a demo application. So we will use the Protege ontology editor, and we will together here constitute an OWL ontology. Okay, so this is the standard part of the lecture, and then we have, of course, some extra parts for you which are not part of the grading of that lecture. But if you are interested in depth into these topics, then you should also have a look at these lectures that are optionally or voluntarily. So for RDFS semantics, of course, we can go a bit deeper. In the first lecture or first part of the lecture, we will only cover, let's say, the very simple notion of formal semantics for RDFS, and we will make clear why it's necessary to have this kind of semantics and how it works in general. But here in 4.9, 0.10 and 0.11 we will go deeper, so you will see the entire and fully fledged semantics, how really RDFS is interpreted by a reasoner. And we will see, of course, this interpretation is rather complex, and you will see the necessity that we have to define something which is called a deduction calculus, which are syntactic rules. Correctness of these rules and completeness always have to be proven. We don't do this, I only show how it works. And we will see a set of deduction rules which can be applied for enabling RDFS semantics. Then in the part 4.12, we will talk about OWL profiles. Also OWL, if we consider OWL together with its compatibility to RDFS, so if all RDFS is included in OWL, then OWL again becomes undecidable. We know that OWL only restricted to description logics without considering RDFS is still decidable. So this is one of the reasons we have already looked at description logics. And the decidability for OWL nevertheless is rather hard, so it's rather time consuming, these algorithms. So therefore one tries to further reduce the complexity to the so-called OWL profiles, where the profiles have a complexity of only polynomial time and not of exponential time, not of non-deterministic exponential time. So they are much faster. We are restricting OWL a little bit. We have nevertheless sufficient expressivity, but all algorithms will become much faster, and this can be enabled with OWL profiles. So we will talk about this in this part of the lecture. And then, of course, we have already talked about rules. You will see a concrete example of a semantic web rule language, which is Swirl. And in the end, we will see Swirl. Of course, if we combine rules and OWL, this is undecidable. You can also look at a decidable fragment of Swirl. And this then we will cover in the last part of that lecture, where we talk about rules which are expressible in OWL. So now, lean back, enjoy the lectures, and have fun.